Your electric motor cannot use the electricity in your battery. Not directly. The battery stores 400 volts of DC, direct current. Steady, one direction, always positive. Your motor needs AC, alternating current, 3 phases, constantly switching direction, frequency changing every millisecond based on how fast you're going. Something has to convert one into the other tens of thousands of times per second with almost no wasted energy, or your car would go nowhere. That component is the inverter, and it's the most engineering dense part of your electric vehicle. Also the most underrated. Today we open it up. Over the last 3 weeks on WattInside, we've covered the anatomy of the EV, the battery pack, and the BMS. Today, the component that turns stored energy into motion. Because a battery without an inverter is just a very heavy paperweight. Let's start with the fundamental problem. Chapter 1. Why AC and not DC? You might reasonably ask, if the battery is DC, why not use a DC motor? DC motors exist. They powered early EVs. Simple, cheap, easy to control. But they have a fatal flaw. They use brushes and commutators, mechanical contacts that wear out. And their efficiency at high speeds is terrible. Modern EVs use AC motors, either permanent magnet synchronous or AC induction. Both need alternating current with precisely controlled frequency and amplitude. Change the frequency, and the motor speeds up or slows down. Change the amplitude, and the torque changes. The inverter is what generates that precisely controlled AC. Chapter 2. The switching problem. Here's the trick. The inverter doesn't have any moving parts. It generates AC by switching DC on and off. Extremely fast. Imagine you have a light bulb connected to a battery. If you flick the switch on and off, the bulb blinks. Now, imagine you can flick that switch 10,000 times per second, and you can control exactly how long it's on versus off during each cycle. Do this cleverly enough, and the average voltage over time looks like a smooth sine wave, even though the actual voltage is just a series of on-off pulses. This technique is called Pulse Width Modulation, or PWM. It's the core principle behind every modern inverter. The switches themselves are transistors, and their quality determines almost everything about how good your inverter is. Chapter 3. The transistor evolution. For decades, EV inverters used a specific type of transistor called the IGBT, insulated gate bipolar transistor. Silicon-based, cheap, reliable, well understood. But IGBTs have limits. They can only switch on and off maybe 10 to 15,000 times per second. Faster than that, they get hot and start to fail, and they lose energy every time they switch. About 1 to 2% of the power flowing through them. For a battery pack storing 75 kilowatt hours, that 1 to 2% adds up to roughly 7 to 15 kilometers of range you're throwing away as heat. Around 2018, a new transistor started appearing in high-end EVs. The silicon carbide MOSFET. Same basic function, completely different material. Silicon carbide can switch 4 to 5 times faster than silicon. Loses far less energy in each switch. Handles higher voltages. Runs cooler. Tesla put silicon carbide MOSFETs in the Model 3 inverter in 2017. It was one of the reasons the Model 3 had noticeably better range than competitors with similar batteries. Today, almost every new EV inverter above 200 kilowatts uses silicon carbide. The industry is transitioning, and the winners are the companies that got there first. Chapter 4. The 3-phase output. Modern EV motors have 3 phases. Each phase is a separate coil of wire wrapped around the stator. The inverter generates 3 AC outputs. Each one is shifted by 120 degrees from the others. When these 3 phases are applied to the motor, they create a rotating magnetic field. And that rotating field is what pulls the rotor around. Change the frequency of the 3 phases, and the rotor speeds up or slows down. Change the amplitude, and the torque changes. Reverse the order of 2 phases, and the motor spins the other direction. This is why your EV doesn't need a reverse gear. The inverter just tells the motor to spin backwards. Same hardware, different software. Chapter 5. Regenerative braking. Here's something inverters do that no combustion engine ever could. When you take your foot off the accelerator, the motor doesn't stop. It becomes a generator. The wheels are still spinning, and they're now pushing the motor around. That generates AC electricity in the motor coils. But the battery needs DC to charge. And the AC from a motor has variable frequency depending on how fast the wheels are turning. So the inverter runs in reverse. It converts variable frequency AC into stable DC, sends it back to the battery, charges it while you brake. This is why one pedal driving works. The inverter is doing the work of a brake and a generator simultaneously. The physical brake pads only get involved for emergency stops or when you come to a complete halt. An inverter that can efficiently do both directions is much harder to design than one that only goes one way, which is why regenerative braking in some cheaper EVs is weaker than in Teslas or Hyundais. The inverter can't handle the reverse power flow as efficiently. Chapter 6. Why the inverter fails. Inverters are the most common expensive failure point in modern EVs. When your car throws a reduced power warning or refuses to accelerate, the inverter is usually the first suspect. Why do they fail? Heat is the main enemy. Every switching transistor generates heat. Multiply that by tens of thousands of switches per second, and you get serious thermal stress. Inverters have their own dedicated cooling loops for this reason. When the cooling system fails or a coolant pump dies, the inverter cooks itself. Voltage transients are another killer. When you slam the accelerator or dump regenerative energy back, the inverter has to handle sudden voltage spikes. Silicon carbide handles this better than silicon, but any transistor has limits. And software bugs. The inverter is controlled by firmware. Bad firmware can command the transistors to switch in ways that damage them. This is why Tesla has had multiple recalls related to inverter software over the years. Replacing an inverter is one of the most expensive out-of-warranty repairs on any EV, between $3,000 and $7,000 plus labor. Some manufacturers make you replace the entire drive unit, which pushes the cost past $10,000. Here's something I want to point out. We talk about EVs as if they're simple compared to combustion cars. Fewer moving parts, fewer things to break. And mechanically, that's true. But the complexity moved. It didn't disappear. The inverter alone contains more sophisticated engineering than an entire combustion transmission. Silicon carbide, semiconductor physics, high voltage insulation, thermal management, precisely timed pulse width modulation. Firmware doing millions of calculations per second. An electric vehicle is not a simpler car. It's a differently complex car. The complexity moved out of the mechanical drivetrain and into the power electronics. When people say EVs will be more reliable in the long term, they're partially right. Fewer things wear out mechanically. But when something does fail, the repair is often more expensive, more specialized, and more dependent on manufacturer support than an old engine ever was. Understanding your inverter is understanding what makes your car actually move, and what will one day cost you $5,000 if it fails. So to recap, the inverter is the component that converts your battery's DC into the AC your motor needs. It uses transistors switching tens of thousands of times per second, controlled by pulse width modulation. Modern high-end EVs use silicon carbide MOSFETs instead of older silicon IGBTs. This is why range keeps improving even when battery capacity doesn't. It generates three-phase AC to create the rotating magnetic field that pulls the motor around. It runs in reverse for regenerative braking, converting the AC from the motor back into DC for the battery. And it's the single most common expensive failure point in modern EVs. Next week, we go into the motors themselves. why permanent magnet synchronous is winning, why Tesla still uses induction in the Model S, and why your EV only needs one gear. If you found this useful, subscribe. Drop a comment with what surprised you most about the inverter. I read all of them. See you Wednesday.